Well, time for part 2, where we get to learn about moment of inertia. What is up with that anyway? I really couldn't tell you why the name is moment of inertia, like, honestly. Now, inertia, that part of it makes sense to me. Inertia is more or less your mass, right? It's your resistance to a change in your motion, right? An elephant has more inertia than I do, and both of us have way more inertia than like an electron does. And that's just based on our masses, right? It's a lot easier to accelerate me compared to an elephant, and an electron moves very easily. There we go. I don't know how else to say that. Okay, so when we talk about moment of inertia, though, that's for rotation. And that is this letter I here, and it represents resistance to rotation, because that's what it is. There's a couple different formulas for it that you're going to see, but the most basic one is I equals sum of mr squared. That's the most basic one. Let me rewrite that black so it'll show up. Okay, so sum of mr squared. What is meant by that is that if you've got a bunch of, let's say, very dense masses, which we call point masses, and you want to figure out, like, what is their resistance to rotation? Their resistance to rotation depends upon a couple of things. Number one, how massive they are, and number two, how far they are from the axis of rotation. Okay, so just a real simple example. If we had a bar with two objects on either side, let's say they're 2 kilograms each, and we pretend that the rod is like basically massless, or at least it's much, much less massive than either of those two objects. Okay, so we'll ignore it. Well, then we would use sum of mr squared to find the moment of inertia. The trick, though, is I can't just say, oh yeah, moments of inertia it's like 4. There's not enough information here. We would need to know how long is the rod. All right, well that's probably important. That might have something to do with r. So if I say it's 3 meters long, that's not enough information still, actually. If we really want to know what the moment of inertia is, we have to specify a pivot point. The moment of inertia depends on where you put the axis of rotation. Okay, so as an example, get something like a metal bar, and don't try and rotate it like this, because then you're also doing things like fighting gravity. Okay, but you can just hold it this way and experience, well, okay, all right, that's not that hard to rotate. On the other hand, if you take it way out here and try and rotate it, right, it's more difficult to rotate. It's also harder to hold up because gravity wants to drag it down. So instead of looking at that, maybe we'll look at something where the object is balanced and I can change how far the mass is from the pivot. All right, so here we have, it's just a wooden dowel. It's 4 feet long. It's so big it doesn't even fit in the, oh, there, no, it does fit in the frame. Okay, and if these are a clump of washers at these two positions. So if I have them here, it's like nothing. All right, that's really easy to rotate. But if I move them way far out to the end, and this one way also far out to the end, and then I try and rotate them, well, then I can feel that's a much more difficult matter. They don't want to rotate as freely as they did before. So based on their distance from the center, the moment of inertia is much greater in that configuration. Okay, so back to the example we were considering. If I put the pivot right in the middle, I'm going to regret this 3 meters, aren't I? Because I have to now square 1.5. Oh, well. Okay, well, the moment of inertia would be, well, this m is 1.5 meters away. Let's call that 3/2. It contributes to the moment of inertia 2 that's its m, times 3/2 squared, all right? And then the other one contributes the same thing. All right, so that's going to turn into 9/2 plus 9/2 is 18/2 is 9. 9 what? Well, in the previous video, we said it was kilogram meters squared, so it's nice to just know that. But if you do forget it, it's also nice to know that it's easy to figure out because this formula just gives it to you. M is, of course, measured in kilograms. R is measured in meters, so kilogram meters squared. Okay, if I put the pivot somewhere else, like let's say not right in the middle, but say here, so it's 2 meters from this one and 1 meter from that one. Now my calculation would look like this. So let's call this point A and this point B. So the moment of inertia through A is 9. The moment of inertia through B would be 2 times the first 2 kilogram mass is 2 meters away. The second one is only 1 meter away. And so the total moment of inertia is going to be, that's 8 plus 2, so 10 kilogram meters squared. All right, if you're thinking to yourself, oh, that's bigger than it used to be. I wonder, why is that? Why is it a bigger number? Could there perhaps be a place where the moment of inertia could be smaller than 9? Because it does seem to change as I move the pivot around. So yes, it does change as we move the pivot. That's the whole point. It also so happens that the moment of inertia is always smallest through the center of mass. All right, that's a thing we're going to have to learn to calculate in a little bit, but experientially, the center of mass is wherever you can put your finger and it balances. Okay, so with equal weights on either side, the center of mass is, of course, the center. All right, and that's all we'd have to really say about that. Fine, so moment of inertia through the center of mass is 9. Moment of inertia a little bit far off from that was 10. It's always going to be bigger as you move away from the center of mass. Okay, now, there's 2 other things that brings up that we got to talk about. One is center of mass, all right, and then what if it's not point masses? What if it's a continuous solid? So like that metal bar that I brought up a minute ago, okay? What if it's an object like that? How do we calculate moment of inertia for something like that? All right, well, for center of mass, the formula for that is that right there. That may look kind of like that one. It's got a sigma, it's got an m, it's got an r in it, right? So it's like the same formula. Not really, okay? The r in that formula is the distance from the pivot point. So actually, probably, it's more wise to not use an r here, but rather to use a d. And you'll see why that, oh no, hold on, is that what I meant to say? No, I mean, whatever. We can call it an R or a D. Okay, but for this one, the R isn't the distance from the center of mass, it's the distance from the origin, whatever you say the origin is. So if I say, for this object right here, the origin is the left end, it's fine, okay? If I say the origin is the right end, that's also fine. If I say the origin is the middle, I'm making a poor choice. Never pick the middle of the object. You always pick one side or the other. That's usually the sensible choice, because if you pick the middle, then you have to talk about like r being a negative number on one side and a positive number on the other, and that's not going to be friendly, at least from a calculation standpoint. Okay, so I said the center of mass is in the middle. Well, all right, let's show that using this one, and then we could mix it up and say one end is more massive than the other. if I pick the left end is my origin. So here's my origin, r equals 0. I got my 2 kilograms there, my 2 kilograms there. For this one, mr would be 2 times 0. All right, for the other one, it would be 2 times, we said the pole was 3 meters long, so 2 times 3 over m total is 4 kilograms. So that gives me 6/4, which is 1.5 meters. In other words, the center of mass is 1.5 meters from this end, which is the very middle of the rod. Kind of unsurprising. All right, if we had a situation where this one was more massive, it's less massive, it's 1 kilogram now. That would change my calculation to this. And so now it says the center of mass is 0.75 meters from the origin that I picked, which would be this end right here. Okay, so 0.75 meters from here, that's here, that would be where the center of mass is in this situation. Yes. No, sorry, false. Mr. Erico, the total mass is different if you change the total mass. Okay, sorry, so 3 over 3, 1. Jeez, what am I doing? Okay, so the center mass is there. 1 meter from this one, 2 meters from that one. There we go, that's how it works out. All right, you could, if you wanted to, rework it for yourself, picking the other end as your origin. Like, what would that do to things? The answer is you get the same result. Okay, now, we said moment of inertia depends on where you pick your pivot point. Center of mass doesn't. Center of mass just is wherever it is. But you don't have to rotate through the center of mass. You can, drive a hole through this pole and have it rotate around right there, or whatever point on it you wish. If you want to, you could drill a hole through one end and rotate around the end. So a moment of inertia depends on where you put the pivot, because the r in this one isn't the distance from one end, it's the distance from the pivot point. So it matters a lot where exactly the pivot is. All right, also noteworthy, point masses are a fiction to start with. Okay, I mean, we will say, oh yeah, there's a point mass in that problem. Usually that means that it's just a small, dense object. But frequently, you'll have a situation where you're going to be rotating something which is a solid object, such as, I don't know, a cylinder or a rod, not through its center of mass. And for those kinds of things, there's a table in your book or table on the internet where you can look up the moment of inertia for things to an extent, okay? If I take a metal rod like that, the moment of inertia through the center of mass, you could look up in your textbook, is 1/12 ml squared, where L is the length of the rod and M is the mass of the rod. Cool. All right, that's what it is. All right. That's only if I rotate through the center of mass, which presumably is the center of the rod. On the other hand, if you rotate it through some other random point, you have to use this thing called the parallel axis theorem, which says this. All right. And in this formula, ICM would be, if we're doing the rod still, 1/12 ml squared, because the moment of inertia is at least that. And then the d here, well, the m is the mass of the object. The d is the distance from the pivot to the center of mass. And so the greater distance you get from between the pivot and the center of mass, the larger that moment of inertia is going to be. All right, I guess we'll continue into another video.